Dear students, now we are studying how to solve problems with the help of symmetrical conditions. So, solving problems with symmetry, it is very easy and it is very important also. So, where we require to apply previous conditions like Kirchhoff's laws and solving circuits with the help of Wheatstone bridges. So, similarly, without using these concepts of Wheatstone bridge and what you call using Kirchhoff's laws or in series or parallel combination of capacitors. So, by using the symmetry concept, so we will check if there is any symmetry which is present in the circuit. So, if I know the symmetry which is present, then we have different techniques of solving this symmetry concepts also. So, which we will study in this class. Okay, so let us see. So, for example, if I take point A and point B, so let us suppose I am supposed to calculate equivalent capacitance between point A and B. So let us consider there are different capacitors which are connected in between A and B. Okay. So therefore, one point which we can write here. So make a note of this symmetrical conditions which I write down here. So if there is a symmetry, along line AB means this line, clear ma? Or there is symmetry along perpendicular bisector to line AB, then all points on the perpendicular bisector to line AB are at same potential. Here ma? So this is a very, very important technique of solving the circuits with the help of symmetry condition. So what he is saying here, for example, if this is the line AB, so along this line, if there is a symmetry, okay, first condition is if there is a symmetry along this line. What is meant by symmetry along this line? So if you see the circuit above this line AB, or if you see the circuit below this line AB, if there is a symmetry, then the line, if I take the perpendicular bisector to this line AB, so on that perpendicular bisector to the line AB, every point should be at same potential. Okay ma? So if there is a symmetry along line AB, and then if you take perpendicular bisector which is present to this line AB, then every point on this perpendicular bisector to line AB, it should be at same potential. What is meant by perpendicular bisector? Perpendicular bisector means a line which is making an angle of 90 degrees to this line AB and which divides this line AB exactly in two halves. That is called as perpendicular bisector. For example, if I take this as my line AB of length 10 centimeter, then this becomes my perpendicular bisector which divides this line into 5 centimeters and 5 centimeters, and here exactly it should be making an angle of 90 degrees. Clear ma? So if there is a symmetry along line AB, then every point which is present on this perpendicular bisector, it should be at same potential. Okay. Similarly, if there is a symmetry along this perpendicular bisector also, if there is symmetry to perpendicular bisector also, what is this meaning of this one? So if this is the perpendicular bisector, this is the right side of this one and this is the left side of this one. If there is a symmetry on right side and left side, then also all the points which are present on the same perpendicular bisector, all of them they should be present at same potential. Clear ma? So if points are present at same potential, then already we have calculated previously how to solve circuits by taking equipotential points. In that method we can proceed and we can do the problem. Are you able to understand? So some more conditions we write here. So what are the conditions we write? So what we write it is the first point is that, so if there are capacitors, clear? So along the perpendicular bisector to AB, then remove them and solve the circuit. This is the first point. Clear ma? So on the perpendicular to line AB, if there are any capacitors, you just remove those capacitors. How can we say that we can remove those capacitors? Because if 2 points are present at the same potential and if you connect a capacitor in between them, charge cannot flow through that capacitor. Because potential difference across both the ends is 0, no? Charge cannot flow between those 2 points. So there definitely you can remove those capacitors and you can solve the circuit. Clear? Second point, if there are no capacitors, along perpendicular bisector to AB, then join all the points which are at same potential and solve the circuit. Okay ma? So if there are capacitors which are present on the perpendicular bisector to the line AB, then what you can do, you can remove those capacitors and you can solve the circuit. Second condition is there, if there are no capacitors which are present along that line, then what you have to do, you have to join all the equipotential points, then also you can solve the circuit. Clear ma? So let us try to understand this one by taking an example. First of all, make a note of up to here, then we will see one example how to solve this one. Okay. See, for example, so this is point A and this is point B. Clear ma? And let this one be the line which is perpendicular to the line AB, which is called C and D. So let us suppose here there is one capacitor, here there is one more capacitor, so C and C. Similarly, here there is one capacitor and from here to here also there is one capacitor. So here there is one capacitor and here also there is one capacitor, and A and B are connected to this battery which is having positive and negative terminals. Clear ma? So for example, let us see this example and let us see what are all the conditions which we have discussed previously. Okay. Now first of all, if I check symmetry along line AB, that is my first condition nama. If I check symmetry along line AB, then above this line and below this line, definitely symmetry is present. Okay. So above this line, if you see, this is the circuit, and below this line, this is the circuit. So definitely I can say along line AB there is a symmetry. Along line AB there is some symmetry. Clear? If a symmetry is present, then which is the line which is perpendicular to this line AB? So line CD. This line is perpendicular to line AB. So definitely I can say this point and this point, they must be present at the same potential. Okay ma? So if there is symmetry along line AB, then equipotential points are present along CD. If there is a symmetry along CD, then also equipotentials are present on CD itself. Are you able to understand ma? Okay. So definitely I can say this point and this point, they are present at same potential. Okay. Now for example, if I draw a circuit like this, okay, then how can I solve this one? If I draw a circuit like this, then how can I draw? Clear na? Very simple. So all the points which are present along this line CD, they are equipotential points nama. So this point C, this point D, and this point E. So potential at point C is equals to potential at point D is equals to potential at point D. All of them, they must be at the same potential. If all of them are at the same potential, can charge travel from here to here? Charge cannot travel. What is the reason? This point and this point, they are at the same potential. But for a charge to pass through the capacitor, definitely some potential difference is required. But potential difference here is not present. So therefore, these capacitors, they are useless. Okay ma? So this capacitor C and this capacitor C, these two capacitors are useless. You better remove them because they are not at all useful. Clear na ma? So even if I remove them also, then total capacitance is not going to change in this condition. Okay ma? So therefore, this is one method of solving. Clear? Then you check a symmetry along this line which is called perpendicular bisector to this line AB. Clear ma? So if you check this line CD, then on the right side of this one and on the left side of this one also there is some symmetry. So if you see on the right side, definitely there is symmetry. 1, 2, 3 capacitors are arranged in this fashion. Similarly, if you see the left side of this line CD, then also 1, 2, 3 capacitors, they are present in the same order which was previously, which is present on the right side. Are you able to understand? So in this condition also, definitely I can say symmetry is again present on the same line of CD. Are you able to understand now? So therefore, this is how we can check the symmetrical conditions. Now let us see. Now again here we have written 2 points. What are the 2 points we have written? So if there are capacitors along the perpendicular bisector to line AB, then remove them and solve them. That's what we have done previously. Clear ma? So if there are some capacitors in between, clear? So just we can remove them. We can remove them and we can solve the circuit. Clear ma? So how can I solve circuit now? So let us suppose this is C, this is C, this is C, and this is also C. So C and C, they are connected in series connection, no ma? So C by 2. These two are in series connection, C by 2. These two are also in series connection, and again C by 2. So therefore, what is the total circuit I got? Total circuit is C by 2, C by 2, and C by 2. This is the circuit which I got. Clear ma? So therefore, C by 2, C by 2, and C by 2, they are connected in a parallel connection. So therefore, a total equivalent capacitance is C by 2 plus C by 2 plus C by 2, which is equals to 3C divided by 2. So I will get equation by using this condition. Now there is a second condition also. What is the second condition? If there are no capacitors along perpendicular bisector to line AB, then join all the points which are at same potential and solve the circuit. Clear now? Now if you see the line which is the perpendicular bisector to this line AB, then there are no capacitors here. Clear now? So I am solving only this circuit, not previous circuit. I am taking only this circuit now. So here I don't have any capacitors between this point, and this point. So therefore what he is saying that all these points, they are equipotential points, no? So you can join all these equipotential points. If I join all these equipotential points, then the same circuit I can draw like this. How can I draw? So this is joining of one point. So this is joining. Similarly, this circuit, how can I draw now? This circuit I can draw like this, and similarly this circuit I can draw like this. Are you able to understand now? Previously this point, and this point, they were present at the same potential, no? So definitely we can join all those points. Clear? Now see what is the total capacitance. So C, C and C, they are connected in parallel. So this C, and this C also, they are connected in parallel connection. So therefore what is the total equivalent capacitance? C, C and C, it is 3C. Clear now? It is 3C. So here also C, 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 it is equal to 3C. Clear ma? So this is the total circuit which we got. Now 3C and 3C, they are connected in series connection. If 3C and 3C, if they are connected in series connection, then equivalent capacitance is 3C divided by 2 only, no? Equivalent capacitance is again 3C divided by 2. So these are the two methods in which we can solve if there is a symmetry along line AB, or if there is a symmetry along perpendicular to the line AB also. Okay ma? So make a note up to here. How can I solve this question? So we are supposed to calculate equivalent capacitance between A and B. Are you able to understand ma? Then we are going to check symmetry along this line AB. So this is my line AB. So above this circuit and below this line AB, circuit is it symmetrical or not? Okay ma? So the circuit which is existing above this line and below this line, is it symmetrical or not? What is meant by symmetrical? Exactly same type of circuit should be present above this one, and same type of circuit should be present below this line also. Is this circuit symmetrical or not? That is the question. Can you say? Definitely it is symmetrical, no? So if there is a symmetry present along this line, clear ma? Then you take the line which is perpendicular to this line. Which is the line perpendicular to this line? This line, no ma? This is the line which is perpendicular to this line AB. Then all the points which are present on this line, they must be equipotential points. What is the meaning of this one? If I take this line, this is the line which is perpendicular to, this is the line which is perpendicular to line AB.
Clear ma? So all points, on line perpendicular to AB should have same potential. What is the meaning of this one? So this is the line AB above which we have symmetry. Clear ma? So we are taking the line which is perpendicular to this line of AB. So if I take this point P, if I take this point Q, if I take this point R, therefore what I can write? I can write P comma Q and R are at same potential. Okay ma? They are present at same potential. Okay. What is meant by they are present at same potential ma? What is meant by they are present at same potential? If points are present at same potential, what do you understand? What do you understand? We understand that charge cannot flow from point P to point Q. Why? Because these 2 points, they are present at same potential. Clear ma? Similarly, charge cannot flow from point Q to point R also. Because again, these 2 points, they are present at same potential. Are you able to understand? So therefore, is there any use of this capacitor and this capacitor ma? Is there any use of this capacitor and this capacitor? There is no use of these capacitors. So just you can remove these capacitors. Clear ma? Because all the points are equipotential points and charges cannot flow between equipotential points if there are any components. If there are no components, then it is a different condition. But if there are some components, then between equipotential points, charges cannot flow. Okay ma? So this is the circuit which we got. So once you calculate this circuit, now can you say ma, what is the answer for this one? Come on, what is the answer of this? So 2C and 2C, they are in series. So equivalent capacitance C. So total circuit will be like this. Clear ma? So this is C and C. So equivalent capacitance is 3C. Because C and they are connected in parallel. That is my required answer. Okay ma? That's it. You answer this one ma? Come on. So we are supposed to calculate equivalent capacitance about line AB from point A to point B. How can I calculate this one? Come on. First of all, about this line, is there any symmetry or not? So this is the line. This is the line about which we are supposed to calculate equivalent capacitance number. So you see the circuit above this line, you see the circuit below this line. Definitely there is some symmetry, no? So what is the arrangement above this line? Definitely below this line also we have the same type of arrangement. Okay. So above this line AB and below this line AB, circuit is definitely symmetrical. Then you take that line which is perpendicular to line AB. So which line is perpendicular to line AB ma? This line is perpendicular to line AB. Clear ma? So all these points which are existing on this line, they are equipotential points. Clear na ma? So what is this line? This is the line perpendicular to AB. So therefore all points perpendicular to line AB are equipotential points. That's all now. So therefore, if I name this a point P, if I name this point as point Q, if I name this point as point R, therefore what I can write? I can write P comma Q and R are at same potential. That is the meaning of this one now. So therefore what can you do? Now what can I do ma? After writing here to here, what can I do now? Just remove these capacitors, remove this capacitor and remove this capacitor. Once I remove this capacitor, now what is the equivalent circuit I got? Clear ma? Now how can I solve this circuit? Sorry, I have removed these capacitors. Sorry. I have to remove these capacitors now. So 2C and 2C. These are the capacitors which we are supposed to remove. Clear, ma? So now which capacitors are in series and which capacitors are in parallel, ma? So these capacitors are in series, these two are in series, and these two are in series. Now first branch, second branch, and third branch, all of them they are connected in parallel connection. So therefore, how can I draw this circuit? So this is a C, this is also C, this is also equal to C. So this is A and this is B. Clear, nama? And all these they are connected in parallel connection. So equivalent capacitance is C 3C. Okay, that is our answer. Symmetry is present along which line, ma? First of all, is there any symmetry or not? OC. What is meant by OC, ma? Symmetry is existing along which line? This is line AB, no? Don't think that this is line A, this is line AB only. So this becomes our line A, this is our point B. Clear, no, ma? So symmetry is present along which line, ma? Symmetry, is it present along line AB, or symmetry is existing along line perpendicular to line AB? Along which line symmetry is existing? Symmetry is existing along the line perpendicular to the line of AB. Clear, ma? So this is the line of what you called line of symmetry. Okay, ma? So this is the line of symmetry. But in this condition also, all the points which are existing on this line of symmetry, they are equipotential points. That's what we have written in the starting condition, no, ma? If there is a symmetry along line AB, or if there is a symmetry along line perpendicular to line AB, then always along the line which is perpendicular to the line AB, points are symmetrical. Clear? So definitely I can say this point P, this point Q, this point R, this point S. So I can write P, Q, R, S are at same potential. Okay, ma? P, Q, R, S, they are present at same potential. Okay. So if they are present at same potential, what I can do? Just I can remove this capacitor, remove this capacitor, remove this capacitor. Clear, ma? So if 3 capacitors are removed, now can you say what is the equivalent circuit which I got, ma? So therefore, what are the capacitors which are connected in series? 4C and 4C in series, 2C and 2C in series, 2C and 2C in series, again 4C and 4C, they are connected in series. Okay, ma? So if they are connected in series, what is the equivalent capacitance? 4C and 4C will become 2C, 2C and 2C will become C, 2C and 2C will become C, and 4C and 4C will become 2C. That's all, no? So this is the equivalent circuit which I got. Clear? Next to 2C, C and 2C, they are connected in parallel connection. So therefore total equivalent capacitance is how much? Total equivalent capacitance is 3C, 4C, 6C. 6C is the total equivalent capacitance. That's what we are supposed to calculate. So find equivalent capacitance between this circuit AB. So we are supposed to calculate CAB. Okay, ma? So first of all, is there any symmetry, ma? First of all, is there any symmetry or not? Is there any symmetry? Symmetry is present along which line? Symmetry is present along which line? Can you say? Symmetry is present. Is it present along line AB, or symmetry is it present along line perpendicular to line AB? Along which line symmetry is existing? Symmetry is existing along perpendicular to this line AB. Clear, ma? About this line, symmetry is existing. So this is our symmetrical line. Clear, ma? So if this is my symmetrical line, then what I can do? Already we have written one condition previously, no? If there are capacitors which are present on symmetrical line, if capacitors are present on symmetrical line, then what you can do? You can just remove the capacitors and you can solve the circuit. Clear, ma? But here there are no existence of capacitors. Okay, ma? So here I don't have any capacitor, and here a line is passing exactly through center of this capacitor. Then what can I do in this condition? Clear, ma? Are you able to understand, ma, here what is the difference between previous questions and these questions? In previous conditions, capacitors were present on the line of symmetry. Okay? But here there are no capacitors which are present on the line of symmetry. On the line of symmetry, capacitors are not present. Clear? So if you see this point here, there is no capacitor at all. Similarly, if you see this line here at this position, symmetrical line is passing through center of the capacitor. Therefore, what I can do? So here how I can solve this problem is, so join points of, or we can write join points which are at same potential, Are you able to understand, ma? So therefore, this point and this point, they are present at same potential, no, ma? Because this is the symmetrical line, and on the symmetrical line, every point will be at same potential. Already we have studied, no? So about this symmetrical line, on every point, potential will be same. Clear? So therefore, what I can do is, this capacitor, I will divide this one into two parts. So this is having how much capacitance, ma? This is having a capacitance of C, no? This is having a capacitance of C. And symmetrical line is exactly passing through its center. So therefore, what I can do is, I can remove this one. Clear, ma? Then I can make one capacitor join at this equipotential point, and one more capacitor to be joined at same equipotential point. Clear, ma? So one capacitor I have divided into two capacitors, and now their respective capacitances have become C by 2 and C by 2. Clear, ma? Their respective capacitances have become how much? They have become C by 2 and C by 2. Why I have made them C by 2 and C by 2? Let us see. Okay, ma? See, ma, C is equals to E naught A divided by D, no? What is the equation for capacitance? C is equals to E naught A divided by D. Okay, ma? So if this is my capacitor, line of symmetry is exactly passing through the center. Clear? So I have made this one into two capacitors whose distance between the plates have become half. Are you able to understand, ma? So C by 2, na? Sorry, this is not C by 2, this is a 2C they will become. Clear, ma? So this is 2C, this is also 2C. So distance between the plates of the capacitor has become how much? Distance between the plates of capacitor has become half. So therefore, so new capacitance will be how much, ma? C dash. New capacitance will be E naught A divided by D by 2. So if it is E naught A divided by E by 2, D by 2, then it is 2 E naught A divided by D. This is how I can write now. So this is equals to 2C. So one capacitor has converted into two capacitors whose each capacitance is 2C. Clear? And all these points, they are present at same potential, Doma. So you join this point and this point. Similarly, you join this point and this point. So therefore, from here I am joining one capacitor. From here again I am joining another capacitor. Okay, ma? So this is how I can draw the equivalent circuit if a line is passing through center of this capacitor. Okay, ma? If symmetrical line is passing through center of this capacitor, then what I can do? This capacitor I can split into two parts. Okay, so distance between the plates has become half, no? If distance between the plates become half, then capacitance will become double. So therefore, this equivalent capacitance of C I have split into two parts, 2C and 2C. Okay, and middle point is equipotential to this point, Nama. So join one capacitor to this equipotential point, another capacitor to the same equipotential point. So this is how I can simplify the circuit if there are no capacitors which are present on equipotential line or on the line of symmetry which is perpendicular to the line of AB. Okay, ma? Now after drawing this circuit, now it is very easier to calculate, no? After drawing this circuit, now can you say how can I calculate, ma? Come on. From here, how can I calculate? Shall I rub this one? Shall I rub this one, ma? Now how can I join them? See here, 2C and C. They are in parallel connection, no? So 2C plus C is how much? 3C. So therefore, this 3C is in series with C. So therefore, how can I say 3C into C divided by C plus 3C? Clear, no, ma? So 3C into C divided by 4C. So CC gets cancelled, 3C divided by 4. Clear? So from here to here, what is the equivalent capacitance? 3C divided by 4. Here also same condition, no, ma? So here also what I can write? So this is a 2C and 2C, which is equal to 3C. 3C and this capacitance is C. They are connected in series connection. So again it is 3C divided by 4. So therefore, what is the equivalent capacitance circuit I can draw here? I can draw like this. Clear, Nama? So equivalent circuit is this 3C divided by 4 and this is C. 3C divided by 4 and this is C. So this is point A and this is point B. So 3C divided by 4 and C, again they are connected in parallel connection, Nama. So 3C divided by 4 plus C is how much? 3C plus 4C divided by 4. So how much it is, ma? 7C divided by 4. So this is 7C divided by 4 and this is 7C divided by 4. Again they are connected in series connection. So therefore this is one capacitance and this is another capacitance, 7C divided by 4 and 7C divided by 4. Clear, ma? They are in series connection, no? So therefore what is the equivalent capacitance? 7C by 4 into 7C divided by 4 divided by 7C by 4 plus 7C divided by 4. So totally it will be how much? It will be equal to 7C divided by 8. That is my total equivalent capacitance. Okay, ma? That's all. Make a note of this one. So this is the given question, ma. Can you say how can I do this one? Anybody? See, we have done this problem previously when this terminal B was present here. Okay, ma? When this terminal was present here, then very easily we have said that about this line there was symmetry. So we have removed this capacitor and this capacitor. So this one and these three lines, they are connected in parallel and we have done the calculation. Clear, ma? But terminal B is not present here. Terminal B is present here. Now how can I do this problem? Can you say? Now how can I do this problem? Any idea, ma? Come on. So if this is the given condition, how can I do this problem? Anybody? Sima, this is the line AB, no? This is the line AB. About this line, is there any symmetry? About this line AB, is there any symmetry or not? Come on, you should answer. About this line AB, is there any symmetry? There is no line, there is no symmetry about this line. Then what you do, you take the perpendicular to this line AB. Clear, ma? So this is the line which is perpendicular to line AB. Clear, ma? So about this line there is some symmetry, no? If you see the circuit which is present on the right side and left side, then definitely I can say that definitely there is some symmetry. Okay, ma? So if there is a symmetry, what I can do, if there are capacitors which are present on this symmetrical line, I can remove those capacitors. But there are no capacitors which are present on the symmetrical line, no, ma? Symmetrical line is passing in between these capacitors. Therefore what I can do? So this is a capacitor of capacitance C. This is also a capacitor of capacitance C. Now what I can do, ma? Just what we have done in the last problem. What we have done. So this capacitance, clear, ma? When line is passing through the center, this capacitance C I can split into two parts, no? I can split this one into 2C and 2C. Why 2C and 2C? Again same concept. C is equals to E naught A divided by D. C dash is equals to E naught A divided by D by 2. Clear, ma? Distance between the plates have become half, no? So equivalent capacitance is E naught A divided by D by 2, which is equal to 2C. So C, I am converting this one into 2C. So therefore what I can do, so just remove this capacitor. So this point and this point, they are equipotential points, no, ma? So take one capacitor 2C, join here. Take another capacitor 2C, join here. This is 2C, this is 2C. This is a C and C. Similarly, what about this capacitor? This capacitor also, you remove this one. Instead of this capacitor, you write two capacitors, which first one is having a capacitance of 2C, join at this point, another capacitance of 2C, and again join these 2 points. Clear, ma? So this is the circuit which I got. Now can't I solve this one very easily, ma? Now can't I solve this one very easily? Can I solve it or not? Clear, ma? So solve this one. 2C and 2C, they are parallel to each other. 2C and 2C, again they are parallel to each other. Clear, Nama? So this total branch and this branch, they are in again they are in parallel connection. Clear, Nama? Similarly, this 2C, this 2C, this 2C and this 2C also, they are in parallel connection. Okay, come on, solve this circuit and say the answer now. Got the answer, ma? See, first of all, you should identify which of them are in series and which of them are in parallel. The charge which enters into this one, Q amount of charge, it divides into 1, 2 and 3 branches. So definitely 1, 2 and 3 branches, they are connected in parallel connection. Clear now? Then the charge which is entering into this one, it enters into these 2 branches. So these 2 branches, they are in parallel, and these 2 branches, they are in series with this capacitor. Are you able to understand? So in that method, these 2 capacitors, they are connected in what kind of connection? They are connected in parallel connection, Nama. So 2C and C, instead of both of them, I can write a single capacitor, which is having a capacitance of 3C. So this one has a capacitance of 3C. Similarly, instead of these 2 capacitors also, I can write a single capacitor whose capacitance is how much? Whose capacitance is 3C. That's all, Nama. Similarly, instead of these 2, I can write a single capacitor whose capacitance is 3C. Similarly, here also, instead of these 2, I can write a single capacitor whose capacitance is 3C. So I got answer up to here. Okay, ma? Next, what about C and 3C? C and 3C, they are connected in series connection, no, ma? So 3C and C divided by 3C plus C. So how much? 3C into 3C divided by 4C. C and cancel, 3C divided by 4. Clear? So 3C divided by 4 and this 3C, they are connected in parallel connection. Similarly, 3C and C, these 2 are also, they are connected in series, number. So again, capacitance is 3C divided by 4. So therefore, how can I redraw this circuit? I can just redraw this circuit like this. Clear, ma? I can redraw like this. So this is 3C divided by 4 and this is 3C, this is 3C divided by 4 and this is 3C. So this is point A and this is point B. Okay, ma? So these 2 points, they are present at same potential, just I have separated them. So that is this point. Clear, ma? Are you able to understand? C and 3C. 3C divided by 4. So this is my 3C divided by 4. To this 3C divided by 4, 3C is in parallel. Clear, ma? And this is my equipotential point. This equipotential point, just I have written separately, or you can join them also, no problem. Then again 3C and 3C, 3C divided by 4. This 3C divided by 4, it is in parallel with 3C. So it is in parallel with 3C. Okay, ma? Now just to do this calculation. So 3C divided by 4 plus 3C is how much? 3C plus 12C divided by 4, 15C divided by 4. That's all, number. If you add these 2 capacitances, then I got 15C divided by 4. So 15C divided by 4 and 15C divided by 4, they are connected in series connection. So this is one capacitor, this is one capacitor. So 15C divided by 4, this is also 15C divided by 4. So this is point A and this is point B. Clear, ma? Then I will get a single capacitor, equivalent capacitor, which is equals to 15C divided by 8. So this is point A and this is point B. So that is my equivalent answer. That's all.